Hello. Hello. Hi. Hi. Uh, hello, Eric. Hi, Newell. And hi, Stephanie, and hi, May. Hi, May. Um, I always feel like I'm saying hi, May, when I say hi, May. Okay. Hi, guys. So this is funny. Is everybody at Prism? If that's what's happening? Are you guys supposed to be at Prism? And do you know what I'm talking about? Um, okay. Wait, and can you hear me? Oh, wait, can you hear me? You can hear me, right? Yes. Okay. Thank you, May. Um, well, this is odd. Okay. Well, um, so, okay. Again, the exams are dribbling back to people one by one, very slowly. I'm very sorry. I mean, some of you in this room, I think, have yours, but most of you don't. They're just coming very slowly, and I apologize, but I'm not going to say, well, I guess I am. Okay. So everybody's, this is weird. This is like the first time anybody's been. It's weird. I'm actually, I think this is the first time anybody's ever been. Well, anyway, okay, I'll just pause for a second. Well, um, okay, no, I want to address that. There's one. It's one. It was an update. No, wait. Oh, so it posted two. Okay, okay. No, these are good questions. Thank you for asking. Let me clarify. No, it was meant to be a fix on the first. Okay, we're probably gonna spend the whole period talking about this. Let me just wait till everybody's like settled in. But these are good questions, Eric and Stephanie. Thank you for these questions. Hold on. And let me fix that. Okay, so let me just say now that everybody's getting settled. First of all, again, the exams are coming back very slowly. Like they're coming back one by one. Some of you have yours back. Most of you don't. They're just like, I don't know why they're taking so long, but they're just falling into your inboxes one by one. I'm very sorry about that. But we're just going to keep going while that's happening. But I'm aware of how annoying that is, to put it mildly. But now, and that's partly why we're doing this extra credit thing. But now, no, the extra credit, which we're going to talk about today, I posted it Monday. We talked about it Monday. It was supposed to be due Wednesday or Thursday or something. And then I made a bunch of major corrections, or tried. Like people found errors and mistakes and confusing things in it. So I put a bunch of corrections. And then because I put the corrections, or because there were things that were confusing, I tried to extend it to Friday and to give you more points for it. It's only supposed to be one assignment. I'm going to look in the Google Classroom and fix it right now. It's not meant to be two separate things. It's meant to be that I was fixing things in the first and just reposted it for Friday, but apparently, but I apologize if there's two in there. That is a mistake. Let me look right now. What's going on? But thank you for bringing that to my attention. Let me see. I'm looking. Oh, okay. Yeah, all right. I don't know why there's two there. I'm going to delete the other one right now. Okay, so it's just supposed to be one assignment. It's now extended to be due to Friday rather than Thursday. It's now extended to be 14 points rather than 12, but it's only supposed to be one thing. In fact, before, and we're going to talk about today, I'm going to try to clarify more because I see that there were things that were, I mean, it's not, well, it is meant to be more work for you. I mean, it is, but it's meant to be like a more, and again, let me say, if there's any confusion, it's extra credit in the sense that, first of all, you don't have to do it. But second of all, I want to promise this, if anybody's listening, like, let me be clear. It is meant to give you more points on your exam grade, even if you haven't gotten an exam grade back yet, or especially if you haven't gotten an exam grade back yet, excuse me. And there's no way this thing can hurt you. This thing, this extra credit thing, which I'm going to give more hints about today, like, I would like you to try to do it all thoroughly and all that. And if you try it all thoroughly, even if you don't do it perfectly, you'll get 14 points. But even if you do make mistakes or get things wrong or something, there's no way it's lowering your score in the exam. Let me just say that again, because I think there's a little confusion. There's no way it can hurt you. It can only help you. The worst thing is maybe if you turned in something by Friday night or you turned in something late that was like all botched and horrible, then maybe I won't give you all 14 points. But it's definitely going to hurt you. There's no way it can make your situation worse. That's the sense in which it is extra. And the reason I extended it to Friday and the reason that I gave it like 14 points rather than 12 is because there was something confusing about it that I'm going to try to address in one moment. Like I'm going to screen share and everything. But before I go any further, in fact, hold on one second. I'm sorry. Before. Sorry, let me just make sure this is not wrong in all of the. This is obviously not. Right. Okay. It's just one there. Okay. I'm just making absolutely sure that it's clear in Google Classroom. Before I will talk about it. Right now. Oh, yeah. It seems like that was. Thank you for catching that error. Okay. Okay. My question before we go on, I'm going to try to help with it right now. Like, I don't know how far you got with it Monday, or I don't know if you're confused about it or not. I'm going to try to walk you through parts of it right now. It's because again, it's not meant to be a test. It's meant to help you with your test score. But let me just ask, can you just give me an electronic, thumbs up or a hand wave if it's clear what I'm saying, that it's one assignment that's due Friday, that's worth 14 points, that it's not two different assignments. It's one. Okay. Thank you, Eric. Thank you, Elizabeth. Thank you, Noel. Okay. Awesome. Thank you, May. And Stephanie. Okay. And just, okay. Thank you, Stephanie and Lizzie. You're good, or not to call, you get what I'm saying. Okay. Thank you. Okay, cool. I love it. All right. Okay. So now this is what we're going to do. I hope this doesn't like bore people to tears or add more stress, but I'm actually going to walk you through it a little bit. Oh, no. That's fine. I didn't know you could do that. Oh, that's interesting, Stephanie. Okay, excellent. I'm going to switch the screen. I'm going to share the screen and walk you through it a little bit. I'm going to walk you just to try to clarify it and all that, because now, I'm adding confusion on top of confusion on top of confusion. So hold on, let me just screen share here. Hold on one second. What? Okay. Okay. Oh, and this is that stupid thing where now I've shared my screen and I've shared my ceiling. That's just what you need. Okay. My ceiling is gone. All right. All right. So look, this is the sheet itself, right? This is what you have in Google Classroom. I'm walking you through it a little bit here. This part on the front page is in principle supposed to be like the background information, the review of what we've been saying in lecture, and principal information you need in order to answer the questions that are coming, blah, blah, blah. Okay, so it gives you the numbers, it gives you the equation, okay, blah, blah, blah. Then we get to page 2, to part A. Okay, so I'm going to talk to you a bit for a second about part A. Part A, hopefully you made some progress on part A when you were working together in class 2 days ago. Like maybe you even finished it. That would be great. Well, actually, let me just ask. I mean, I'm going to say things about it either way, but I'm curious. Is there anybody in the room that feels, and I'm not going to put you on the spot to ask you your answers or anything, but is there anybody in the room right now that feels that they finished part A of this sheet? Is there anybody that feels that they did not yet finish part A of this sheet? Wait, so Lizzie is maybe, that's a yeah, okay. But anybody else besides Lizzie, like, can you give me a thumbs up one way or the other so I know you're like, Raise your hand if you did not yet finish part. I'm not putting you on the spot. I'm just trying to figure out how to teach this. So raise your electronic thumb if you are not yet finished with part A of this sheet. Okay, I appreciate the honesty. Okay, cool. Okay, so now I just know I won't be wasting your time when I say some things about it now. Okay, so look, but you should stop me. Okay, cool. Thank you, Stefan. Thank you, all of you. I appreciate that. All right, so part A, like that's on the screen right now, right? Excuse me. Part A, on the one end, is a plug and chug. It is a repeated computation. It's like you do the same type of computation 5 times, and each time you do that computation, you're taking the numbers that are given right there, and you're plugging in into this equation right here in the center of the board, the equation that says F equals plus or minus KQQ over R squared. I'll tell you right now, that's a vector equation. Like there's a vector symbol on the left-hand side of the equation. There's a vector symbol on the right-hand side of the equation. Those are there because ultimately force is a vector. It has magnitude and direction, and the unit vector R is being used to connote a particular direction. But all of that we talked about in the lecture class like 2 Wednesdays ago or something like that. But to be clear, when in the question A, it's just asking for magnitudes. Excuse me. Question A. Yeah, question A is really just asking for numbers. It's just asking for magnitude. So don't let those vector symbols intimidate you or throw you off. What we're really saying in part A is it's giving you a positive point charge of 50 coulombs. Like you're imagining like a whole bunch of protons like jammed together into this tiny space sitting at some location in the lab. So you got a bunch of positive charge all crammed together into like a Euclidean point, into a tiny dot somewhere in the lab. And that amount of charge is positive 50 coulombs. That's what it's asking you to imagine. Okay. And then it's asking you to imagine that you look at some location like 5 meters away from that 50 coulomb charge, 5 meters away. And each of the 5 questions here in the center of the screen is just trying different examples of what type of test charge or what strength of test charge we might find located at that position 5 meters away. In other words, in example 1, the test charge is positive 3 coulombs located 5 meters away. So literally all we're asking, I mean, I don't want to trivialize it, but all we're asking in question 1 is we're saying, oh, I'm going to look in the chat in a second. I see that. 1 second. Sorry. But I'm scrolling back here. I'm saying literally assume that capital Q1 is positive 50. Assume that lowercase q2 is positive 3. Right, positive 3. See, assume that R, the distance between them, is 5 meters. Okay, and assume that K, we always assume that K is 8.9, approximately 8.99 times 10 to the 9th Newton meter squared per coulomb squared. So again, don't even be intimidated by the vector symbols or anything like that at this point. It's just asking you to plug in 8.999 times 10 to the 9th for K, to plug in positive 50 for Q1, to plug in positive 3 for Q2, to plug in 5 meters for R, and then square that, and just multiply and divide all the numbers together and get an answer for F, like how strong the force is. Okay. And if it's asking, since it's technically asking for magnitude and direction, the magnitude is what you're solving for with all those numbers. And direction, I can tell you right now, in each case of this example, direction, there's only 2 choices. The direction is either pointing from Q1 to Q2, like the direction is either pointing from the source to the test, or it's pointing from the test to the source. In other words, the direction is either a push or it's a pull. How do you know? Well, it's a push if the charge is if it's repulsion, it's a pull if it's attraction. In other words, it's a push if both charges are of the same type. It's attraction if they're of different type. So in example 1, for example, I'm scrolling back and I will look, I see there's things happening in the chat. I'm going to look in the chat in 1 second. Sorry, just before I lose my thought. If you look at question 1, where like in all of the questions, in all of questions 1 through 5 for part A, in every single one, the source charge is positive 50 coulombs. And the distance R is 5 meters in every single case. The only thing that's changing is what value we're picturing for the test charge. Let me back up again and say, and I know there's things in the chat, sorry, but let me back up again and say, by source, I mean the charge sort of creating the force, doing the force, pulling or pushing, whereas the test is the receiver, the one being pulled or being pushed or experiencing the force. Okay, so in every single one of these situations on purpose, the source is the same. The source. So this is kind of like you're just doing different trials in a lab. You've got a source sitting there and you're studying some location 5 meters away from the source, and you're just placing different things at that location and seeing what happens. Okay, so in example 1, you're plugging in positive 50 for Q1, you're plugging in positive 3 for Q2, you're plugging in 5 for R squared, for R, and then squaring it. You're plugging in 8.99 times 10 to the 9th for K, because you always do. You run all the numbers together, and you're going to get a number. That number is the magnitude of the force for question 1. And the direction for question 1, well, since it's a positive source and a positive test, the source is pushing the test. It's repelling it because they're both positive. So the answer to direction would be away from the source. So you're going to get some answer, some number, which I'm not telling you now. You can do this on your own, or if you're doing it right now, you can ask and I can check or whatever. But you're going to get some number of newtons and some direction, either from pushing out from the source or pulling in toward the source. And that's going to be your answer for question 1 of these 5. But I am trying to say it's a plug and chug. It's not a trick question. Now, I want to say more about that in a minute. I want to explain why then we ask almost the same question 4 more times. I'm going to explain this again. Let me just look in the chat, though, because things I think are happening in the chat. Oh, good. Oh, good. Oh, okay. Oh, these are great. Oh, these are great questions. Oh, you like totally are paying attention. Thank you. Okay. So, and maybe I might have even accidentally already answered one, but no, Elizabeth's, Stephanie's, and May's question in the chat are great. So I'm going to go in an opposite order of these questions. First of all, May's question, do we use 50 for Q1 for all the examples? Yes, totally yes. For all the, and we're all talking about part A here. Everything I'm saying right now is about part A of this whole sheet. Okay, we'll go to part B in a second, or in a few minutes. But yes, for part A, you're plugging in 50 for Q1 for all the examples. Only thing that's changing from example to example is Q2. Okay, that's totally good. Yes, correct, May. Second of all, on Elizabeth's and Stephanie's question, very fair question. For this question for part A, well, I guess, okay, I'll answer Stephanie's first and then Elizabeth. Like, it's very fair what she's asking. It's not a stupid question at all. But the answer is no. So she's asking, Stephanie's asking, do we plug in 5 for the R at the end too? The R hat, that R with a caret over it. We had one lecture on this like about a week ago or so, but I know this is new to people. That R with the caret over it is called in physics R hat, which I know is so like silly, but I mean, that thing is called a hat. I mean, which is ridiculous. But, and the R hat is important and it does mean something, but right, you don't plug in 5 for that. You only every single, okay, I'll get to that in 1 second. Good question. Good question, Xiaowei. I'll get to that in 1 second. But you do, so you plug in 5 every time for lowercase r in the denominator, just r itself, but you don't ever plug it in for r hat. Here, a quick, and I will get to Xiaowei's question in a second, and I'll get to a larger, well, so this is now about, so you never plug in any number for r hat, like not in this case and not ever. But then that brings me to Elizabeth's with an S's question of like, well, is R hat important? Like here, what's it doing? It is true that in part A, you're not really directly using it. Like, let me try to remind you or re-explain what R, I mean, where it really comes into play is the next page of this whole assignment. But what R hat, I'm just thinking if I should switch my screen in a second. Well, in a second, I'm going to switch the screen, but R hat, literally what R hat means is R hat is the unit vector for R. R hat, like always in physics, is defined to be R vector divided by R. Like let me see if I can write. No, I probably can't write that on the screen. I'll try to write that when I switch the screens in a second. But the definition of R hat always, I mean, you do want to maybe try to please write this down if you can understand what I'm saying. R hat, triple equal sign, like R hat always equals R vector, like R with an arrow over it, divided by plain old R. That's the definition of R hat. Now, what does that mean in English? Like, what's the point of that? What a unit vector always is a vector divided by its own length. A unit vector is a vector divided by its own length. So a unit vector is always a vector that points in a particular direction, but has a length of 1. Like R hat is what we get when we divide R arrow by R itself. So if R arrow, what is R arrow? R, the vector itself, is the displacement from the source charge to the test charge. It's an arrow that points from the pushing charge to the pushed charge. Like that's what R arrow is. R vector is the vector of displacement. It's that points from one charge to the other. So it's displacement. It has distance and direction. Let's say, for example, that R arrow was a displacement of 5 meters in the northeast direction, like in 45 degrees northeast, like for example. Then what R hat would be that vector, 5 meters pointing at 45 degrees northeast, divided by 5, which sounds silly. It sounds almost like dumb, but what's the point of that? Well, then we would get what R hat is a vector of 1 meter pointing at 45 degrees northeast. The point of R hat is that it's the pure direction of R. It's a way of denoting the direction of R without capturing any magnitude of R, just like of R vector, just like R. So the R in the denominator is the pure size of the vector R. It's just the size with no direction at all. It's that size 5 that you square to do your calculations. But R hat is the pure direction without any size. It's just there to tell you what direction the whole force points in. And that R hat in the equation is just telling you that the E field will point in the same direction as the displacement from one charge to the other. It's there to say that the direction of the field points in the same direction as a line that you could draw connecting one charge to the other charge. So the R hat is there purely to denote direction. It doesn't have any size, so you don't plug in 5 for it. You only plug in 5 for the R in the denominator. You don't plug in 5 for the R hat. Again, I'm yelling because it's like a really important point. It is not at all a stupid question. It's like a very smart question, but I'm trying to make the answer clear. So in short, or to Stephanie's question, I'll look at that in a second. To Elizabeth's first question, what I'm ultimately saying is for the calculations you do for part A, right, you won't really use R hat to do anything in part A. R hat, in each one of your answers to part A, all you have to say about direction is whether the force points from the 50 from the source to the test or from the test to the source. That's all you have to say. So you don't really, you're right. The R hat is not actually, it won't change your computations or your calculations or your answers for part A. Where it'll really come into play is the second part of the whole sheet, which I will get to shortly. So hopefully that sort of answers the question. But then I also want to answer Xiaowei's question, but then also, wait, but there was another, R hat should be a sign. I'm not sure what that means exactly. R hat. Okay. R hat should be a sign. I'm not sure exactly what to say about that. I mean, what the signs are doing in this context, like ultimately positive means push, means repulsion, and negative means pull, like attraction. So, I mean, you're not going to have R hat in any of your, or you don't have to have R hat in any of your answers really for the first part of this sheet. And your answers could have negatives or positives in them, I suppose, although it might be even just clear to say push or pull. I'm not sure if that's answering that, but now with Xiaowei, but I'm still going to say more about the whole sheet. Don't worry, like we're not walking away from the sheet, but just on Xiaowei's question in the chat now, what is E and E? Okay, capital E stands for electric field. That's where I'm going next with all of this. Like the whole purpose of the whole sheet really is ultimately to show you how the electric field or electrostatic field works. So that's where I'm going next. So you don't have to do anything with capital E to get the answers to the first 5 questions on the second page of the sheet. You'll use capital E on the next page, so I'll get to that. But lowercase e is really lowercase epsilon naught, and that's a universal constant. That's a funny different way of writing the 8.99 number. To be totally blunt, you can ignore that lowercase e right now. You don't need it to do any of these calculations. I'm just having to be honest with you because K is often written in this funny, complicated way. K is a constant. It's often written as a combination of other constants for reasons that we may or may not get into. We're not going to get into today. So, and I just have to be honest, letting you know that because it comes up all the time, but you don't really have to worry about lowercase e, the epsilon naught right now. You just have to know that K is approximately 8.999 times 10 to the 9th. I don't know if that helps or not, but I'm going to, so hopefully these are answering the questions, but I'm going to keep talking about like what to do in this sheet. Okay. So I'm still here in part A. I'm saying that in part A, in lowercase Roman numeral 1 of part A, you would literally plug in 50 for Q1, you'd plug in positive 3 for Q2, and you'd plug in 5 for lowercase r. And you know what I'm even going to say? Look at the time. I think let's pause for a second. I would like everybody to just literally do that. Just that one right now, because everything I'll say about the rest of the sheet is going to make things a lot clearer, frankly. So let's all just pause. You don't have to go to breakout rooms or anything like that. But can everybody just do that quietly? Just do that calculation of I'm just talking about. Could everybody just do that? The thing that I just boxed right now on their piece of paper. You are plugging in to, you're going to use those numbers and plug into, can I scroll this? You're going to plug in to the F equation up above. And I'm even going to say, I'm going to pause, I'm going to shut up. Everybody just do it quietly. And just when you either have an answer or you think you're stuck, when you're done one way or the other, either with an answer or being totally stuck and having a question, please, everybody, when you're ready, put something in the private chat, or I mean, it could be public if you want, but just let me know whether you either have an answer or whether you think you're done one way or the other. Okay. And I'm going to pause for a second. And I'm going to, pardon me. Oh, nice. Wait, sorry. Yeah, I think your answer for yes, your answer for this one should be positive. Yes, and I'm responding to anybody in the private chat. Anybody who put an answer in the public chat, I'm definitely saying awesome that you put an answer in. Thank you. I'm not going to say whether it's right or wrong. So other people, because I do want everybody to try this. I want everybody to tell me one way or another, either in private chat or public, either give me an answer and I don't care if it's wrong. Believe me, I'm not. And remember, if you get it wrong, you can submit that for extra points anyway. But I do want to hear from everybody, whether it's an answer, a right answer, a wrong answer, or a question, or even just like, I'm totally stuck. I just do want to hear from everybody. And like Elizabeth L, I'm totally congratulating for putting an answer in the public chat sheet. And remember, you can always submit these things for points. You know, there's all these participation things for this kind of moment. So definitely Elizabeth is like gonna, and there's other people, but they're just private. I'm not mentioning them by name. She definitely can submit this for points. I'm just explicitly not saying whether she's right or wrong so that it doesn't jump the gun on anybody else. But I'm totally acknowledging that she put an answer in. Oh, I don't mean Elizabeth. I do mean Elizabeth. Yes, yes, yes. But I do agree that it should be positive. So I'm just going to wait till everybody does something, whether it's public or. So again, I'm just going to. So, and I'm just going to say, I would like to hear from everybody one way or the other. You can just type, you can write me and say, I'm stuck, or I'm sorry, or I'm spaced, or whatever. I won't hold it against you, but I just want to sort of account for everybody here because it's a small enough class. There's no reason not to make this work. And I will go over it. Like, again, I'm not going to do this whole sheet for you, but I want to at least get you to see what, it's not that bad once you see what to do. So, so all right, awesome. So again, I'm totally congratulating Lizzie for saying something in the chat. I'm not going to say whether it's right or wrong, Although I am going to note that it seems very similar to another number that was in the chat recently. And so again, I would like to hear, so people are either calculating right now or, and I understand your thoughts could be a mile away. I just want to hear something from everybody, even if it's just like, even if you just type in the chat, please just teach this or whatever. I just want to hear an acknowledgement. Thank you. Okay. Okay, I think I've heard from most people. Oh, wait, let me see. Okay, I'm going to. Okay, I'm going to start. Okay, so number one, I do appreciate that everybody's participating. And I got some of these answers in the public chat. Like, let me start by saying I do agree with the answer that I got a couple of times in the public chat. Like, I do think that the answer is approximately 5.4 times 10 to the 10th newtons. Okay, this is a force measured in newtons. I'm not correcting anybody, I'm just saying. And it's an enormous force. Like, it's like, yeah, 5.4 times 10 to the 10th to the 10th to the positive 10th newtons, because that constant 8.99 times 10 to the 9th makes everything so high. In other words, and this is like I mean, granted, this is a lot of charge. A 50 coulomb charge is a very strong amount of charge. It's a lot of charge. Like, don't forget the charge of one single proton. The charge of one proton is like 1.60 times 10 to the negative 19th coulombs. So I mean, it would take like 16 I was going to start 16 billion, trillion, quadrillion, quintillion. It would take 16 quintillion protons to make 1 coulomb of charge, and this is 50 coulombs of charge. So it's a lot of protons sitting there, but they're exerting a very, very, very strong electrostatic force. The electrostatic force is a very strong force. Just that's one thing that these numbers indicate. Like I do agree with the answer 5.4 times 10 to the 10th newtons. That's enormously high because this is a lot of charge, but also because the electrostatic force is enormously strong. Okay, so hopefully at least most of the people who are like with me right now see that question number one is basically just a plug and chug. You just write, I mean, you insert those numbers into that equation. You get a magnitude of approximately 5.4 times 10 to the 10th newtons. And the direction, you could call it positive, or you could say it's a push, or you could say the direction is from the 50 coulomb, pointing from the 50 coulomb charge to the 3 coulomb charge. Now, that's the answer you get for number one. Hopefully that helps everybody. Now, I'm not going to do every single one for you, but let me say a couple of things. If you then go on to number two, you'll notice and this goes back to now what May was saying 20 minutes ago. If you go to number two, you notice it's the exact same question with all the exact same numbers, except the only thing we've changed is the magnitude of the receiving, the test charge, the charge that's experiencing this force. We've changed it from +3 to -6. Everything else has remained the same. So we've changed the Q2, the lowercase q2, in the numerator of the force equation. On the one hand, you could just totally redo the whole calculation again. Like you just plug in the new numbers, just like you did in part one, you could do it in part two, and you'll get a new answer and it'll be correct and you'll be fine and correct. And you could then keep doing that for the next 3 examples and it would be fine. Like it's not a trick. I am asking the same question over 5 times with only one fact changing each time. And the fact that's changing is the amount of that test charge. So to put it one last final way, you could imagine that this is like an experiment. Oh, there's something in the chat. I'll check out the chat in 1 second. My apologies. But you could imagine that this is an experiment where we have this big ball of protons sitting in the middle of the lab at a certain location. And then 5 meters away, we're doing different trials with different little things that we're putting 5 meters away. First, we put like a little bit of like 3 like protons, and we take them away. And in the next case, we put like 6 like electrons. And then the next case, we take those away and we put like 5 protons. And each time we're measuring the force that our little test object is experiencing. And we're getting different force measurements each time measured in newtons. So it's the same exercise that we're doing over and over again, just getting different results each time. So for sure, and it's meant to make a point, it's meant to illustrate something, which I will explain in a moment. But for sure, if you just end up finding yourself doing the same calculation 5 times and just getting 5 different answers, then yeah, that's all I'm asking you to do. It's not meant to be a trick. There's a reason I'm asking you to do it. And that's what I want to explain in 1 second, but there seems to be something in the chat. So let me look. Hold on a second. Right. Oh, that's why you got a different, oh, that's really great, May. Your honesty. Now I see why you got the answer you did. But right. So I'm saying to do this calculation, this is what I was sort of trying to explain at the beginning of class. The R hat at the end, R hat is different from just regular R. R hat is a vector that points in the direction of R, but has a magnitude of 1. Like the value of R hat is always 1. So even if we did technically multiply by, we would just be multiplying by 1. The only 5 that you use for R is in the denominator of the fraction. So, and I see why you got the answer. So, okay, to everybody. So you don't multiply, you don't plug in 5 for R hat. That's right. A good point. But okay, if that's clear. Oh, wait. Oh, so did I answer your question or no? Oh, okay. Okay, cool. Okay, thank you. And again, those of you just not to, especially if you're worried about points or grades or whatever, please remember, any one of you who asked a question in this class, like you could submit that for participation, but then I answered it and you said, okay, thank you, or whatever. Remember, that counts as closing a conversational path. Like that's a different set of points you can get just for the fact that you said, okay, thank you. Like, if you're looking for points, they're there to get. But anyway, all right. So we did that calculation in number one. We got an answer. I'm telling you the answer. Actually, you guys have told me the answer, like Lizzie and others and Elizabeth and Stephanie told me the answer, which is approximately 5.4 times 10 to the 10th newtons. Now we go to exercise 2. Here's where, and you could just redo your whole calculation from exercise 1. You could just replug in all the numbers again. Or since we're doing this sort of together right now, or you might notice something. You might notice that in exercise 2, all I've changed was the value of lowercase q2, right? I've swapped out a positive 3 coulomb test charge and swapped in a negative 6 coulomb test charge. So you could redo the whole calculation and that would be totally right and you get full credit, no problem, and you get the right answer. But you might notice if you're a little bit maybe smart or a little bit lazy, which is the same thing as smart in a way in math and science, you might notice, I don't feel like doing this whole freaking calculation again. You might notice, wait a second, force is directly proportional to charge. F is directly proportional to Q2. So if all you ever about is changing in the facts here is Q2, and all he's really doing is taking the old Q2 and multiplying it by 2, and then, multiplying it by -2. He's multiplying it by 2, and then he's multiplying it by a negative sign, by -1. You might say to yourself, couldn't I save myself a lot of hassle and a lot of computation by just taking my answer from question 1 and just multiplying that by 2 and adding a negative sign? You might think to yourself, if I said the answer for question 1 was 5.4 times 10 to the 10th, couldn't I just say that the answer for number 2 is negative 10.8 times 10 to the 10th, which is the same thing as 1.08 times 10 to the 11th negative, right? You might think of that as a trick to just get out of all of this onerous computation. And let me tell you right now, you'd be right to think that. You don't have to do that. But if you follow what I'm saying, because this is a point that I'm trying to develop with this, there's a reason we're doing this repetitious thing like 5 times. If you notice that it would save you a little time and a little hassle by just taking your first force answer and multiplying it by 2, by -2, because all I did was take the first test charge and multiply its magnitude by -2. And if you know, and force is directly proportional to charge. So if you think you could just take your answer from number 1 and just multiply it by -2 to get your answer for 2, you'd be correct. And you can totally do that. And you'll get the right answer. You get the same answer as anybody who just redoes the whole calculation. Either one is fine. Okay, please just make a note of that. Just note that would work. So what? So now we get to question 3. We get to question 3. And we're asking, okay, again, we leave everything else the same, but we take the test charge out and we substitute it in with a value of +5. So you might say now, okay, can I do my trick again? Like, I don't want to keep doing these stupid computations. And maybe Avram is like asking me to notice a pattern or something like that. So you might say, can I do my trick again? And just kind of like multiply by 5. But then like multiply my last answer by 5 or something. But then you notice like, oh wait, this is kind of annoying because like, it's not like the charge is 5 times as great as my last answer, right? My last answer was based on a charge of -6. Now the charge is +5. I can't just like multiply my last answer by 5. If you see what I'm saying, I can't even multiply my first answer by 5. I would have to like divide my first answer by 3 and then multiply it by 5. Do you follow what I'm saying? Like if you wanted to get out of redoing the calculation, you could, if you notice that this new test charge is like 5/3 as strong as our original test charge. So you could like divide by 3 and then multiply by 5. But you might say to yourself, and if you did that carefully, you would get the right answer. It would work. Or you might say to yourself, well, now that's a lot of trouble. Like this was meant to be a trick to help me reduce computation. But now if I'm like dividing by 3 and multiplying by 5, like that's such a hassle in itself. I don't even know if it's worth it. So you might do it or you might not. And it's totally your choice. You could do it one way or the other. But see, that's when we get to question 4. This is the reason that I'm sort of putting you through this to see, I'm putting you through this one time and one time only to see a pattern, is that what you might notice is, you know, all of these computations would be really easy if I had just started off, with the answer, with assuming that the test charge had a value of 1. If I had done that first, then all these answers would be really easy to get. If I now in question 4, it asks you to get, what if it's a value of 1, right? If you do that, if you just answer the question for 1, then no question, you can do the very last example, like the -2, really easily by just taking your answer for 1 and multiplying it by -2. And you could do any of them easily. You could have done the 5. In other words, by the time you get to 4, and I see there's something in the chat, I'll look in the chat in 1 second. I'm not doing this to mess with your mind. I'm doing this to show you something, that we could do force calculations afresh each time. We could do force calculations one at a time, one at a time, one at a time. But after a while, we start realizing that there's a little bit of a shortcut that we could do on these force calculations. After a while, we realize that as long as all we're doing is changing the value of the test charge, we can just keep adjusting the value of our force answer. But it's easiest to do. It sort of takes us a couple times to realize, but the easiest thing to do, like the best force calculation we could possibly do, is figuring out what the force would be acting on 1 coulomb of charge. Because once we get that, once we get the answer acting on 1 coulomb of charge, then no matter what anybody throws our way for the test charge, we just multiply by that. Like if they give us a 2 coulomb test charge, we just multiply our answer by 2. If they give us a -7, we multiply our answer by -7. In other words, by question 4, by the time you realize going from question 4 to question 5, how much easier life is, it's meant to make us realize, and I will pause for a minute, I'll look in the chat, but what I'm trying to show here, you can get the right answer by just doing it straight up each way. But I'm trying to show that there's something very useful, something that will get you out of a lot of hassles. Whenever we stop and just do the force calculation on a test charge of +1 coulomb. Once we get that answer, all other force answers are a lot easier. So it's good to have that information just on our piece of paper first and foremost. Okay, I'm going to pause for a second because there's something in the chat. Hold on a second. Oh, cool. All right, that counts for class participation, Elizabeth. All right, cool. Thanks. Okay, so I'm going to keep going. So you do those 5 calculations. Again, even if everything, I mean, hopefully what I'm saying kind of does make sense. And hopefully it's at least showing you why I'm asking these questions. But even if everything I just said sort of went in one ear and out the other, you do those 5 calculations. And at the end of the day, what I'm saying then, if I scroll here, what I'm saying is, okay, the answer that you got for number 4, like maybe even, I don't know, like circle it or make a note of it. Whatever answer you get for number 4, that is ultimately what we mean by the field. I mean, now this goes back to Jiaowei's question before. This is the difference or the distinction between F and E. F is the force that one charge exerts on another charge. E is the field that the first charge just exerts. E is the field. What we mean by that is the amount of force that the source charge exerts on to every 1 unit of positive charge. It's the force per charge. So like it's the amount of force measured in newtons that would be exerted at a certain location if all that were sitting at that location were a test charge of 1 positive coulomb. The field is what would happen to 1 positive coulomb. And the purpose of the information is, it's really, in a way, it's us saying, like, you know what? We don't need to know. Like, if we ever were to put 2 coulombs there instead of 1, if we were to put 2 coulombs of test charge there at that location, we would just take the field answer, the answer that we got from the field, and just multiply it by 2. In other words, what it's trying to say here what it's trying to say right here is field is force per charge. E is F divided by Q. Therefore, you could rewrite it. You could say, therefore, F is Q times E. If you ever want to know what force is being exerted on some certain amount of test charge found at some location, just take the number of the field at that location and multiply it by the amount of the test charge. So what the field is all of the information contained in the original source charge and the location of the original source charge, like relative to some point in space we're looking at. The idea is we're saying once you put a source charge, once you put a 50 coulomb positive charge, for example, like somewhere in the lab, what we're saying is somehow that 50 coulomb test charge places a bunch of vectors everywhere in space. At every point in space, it places a little vector. The size of the vector contains all of its information, like it's 50 and it's R, like how far away it is, squared divided by, multiplies by the constant. So there's a little arrow at every point in space. The size of the arrow indicates all of the magnitude of the charge creating that arrow, and the direction of the arrow points either directly to the charge or away from the charge, depending on whether it's a push or a pull. So every time we put a source charge somewhere in space, it spreads out arrows everywhere in space. I mean, it doesn't literally put arrows in space, but it puts a vector representationally at every point in space around it. It places the information describing it at every point in space, so that if and when any other object ever comes along and finds itself at some location in space, it lands in that information created by the original charge. The field is a field. The field is an array of information everywhere in space created by any object that's in space. The field is the mechanism or the medium or the carrier or the agent that's containing and transmitting all the information describing what's happening over here in space to any and everywhere else in space. The field is the information describing what's going on, okay? So field is force per charge. It's the amount of electrostatic force that would be exerted on every 1 coulomb of charge that would be or could be found at any given position in space. Force is measured in newtons. Field is measured in newtons per coulomb, okay? That's what all of this is trying to get you to see, this first part of the sheet. But then now, so last way to put it, force is something I do to you. One object exerts a force on another object. Field is something one object does to space. Force is a relation between 2 objects. Field is a relation between 1 object and space. Force is KQ1 times Q2 over R squared. Field is KQ over R squared. It's all the information of the force except for the information of Q2. That's what field is. Now, getting to the second part, which is a little bit more complicated or a little bit more involved. All that is to say that, so a field is, another way of saying field then is it's a vector valued function. The field due to the source charge is a rule that says for any given location in space that you name, any position in space that you name, there's a vector there with a certain length and a certain direction representing the electric field magnitude and direction at that point in space. Well, when we get to, all right, so yeah, so that's what thus the electrostatic field will be the amount of force that, okay, so that paragraph at the bottom is what I was just saying. Now, we get to the second part. Oh, let me say, this second part of the sheet now puts it says, imagine an XY plane, like, imagine a two-dimensional region of space. And we have two charges somewhere in that plane. We have charge 1 called Q1 that has a charge of positive 5 coulombs. We have charge 2, Q2, has a charge of negative 2 coulombs. And they're located at these different places in the XY plane. Like charge 1 is at 5,4. Charge 2 is at 10,3. Oh, so this was the sheet that I gave you on Monday. But one thing is, a couple people noticed there, or I noticed there was an extra column in the chart in the sheet that I gave you on Monday. The extra column was totally confusing. It was actually a mistake, and it probably threw people off. So I've just chopped off that last column. You don't need it. It was a mistake. But this is one of the corrections that I made to the sheet. Again, this is the same sheet from Monday, but it had corrections. One correction is that the chart no longer has that last column because the last column was a mistake. Okay, so we have these two charges in the XY plane, and then the location of interest, the place that we're interested in measuring the field is 0, 0, the origin. So part A says, draw a neat and clear sketch of the situation as you understand it. The sketch what I mean by a sketch is, I want at the two different points that were given, the charge 1 and charge 2 at point 5,4 and at 10,3, at each one of those points, each one of those points is causing electric field. That means it's making vectors everywhere in space around it, including at the origin. So what I want for the sketch is, I want you to draw an arrow connecting each one of those dots to the origin. Basically, the drawing that I want in A is 2 arrows, 2 vectors. One vector that connects charge 1 to the origin, and the other vector that connects charge 2 to the origin. Now I'm going to tell you right now something about the answer. If you're still paying attention to me, Cork, bless America, this will help you with the answer. All I want for that sketch is 2 arrows. But the question is which, and they're each going to point, they're going to connect the charge to the origin. The question is, what way should the arrows point? Well, charge 1 is positive. So let me back up for a second. We're ultimately, the goal of this whole problem is to figure out the field at the origin, to figure out the magnitude and direction of the electric field that is occurring at the origin due to these 2 charges. Field means, remember, figuring out what force would be exerted if there were a positive 1 coulomb of test charge located at the origin. So you're imagining in your mind, you're not drawing it, but you're imagining in your mind that there's a positive 1 coulomb of charge sitting at that origin, experiencing forces from these 2 charges. Imagine that it is positive. If it were positive, do you see it would be pushed, it would be repelled by charge 1, because charge 1, Q1, I mean, is a positive charge, right? Whereas it would be attracted to, it would be pulled by charge 2, because charge 2 is a negative 2 coulomb charge, right? So what I'm saying, I'm about to give away the answer here, but I just want to make this clear. I'm saying you're going to have an arrow pointing from the coordinate 5,4 to the origin, and you're going to have an arrow pulling away from the origin to the coordinates 10,3. Okay, I'm saying the arrow from Q1 is a push because Q1 is positive. The arrow from Q2 is a pull because Q2 is negative. And that's the whole sketch that I want for part A. That's all I want for part A, is those 2 vectors, like, in the XY plane labeled, like with all the points labeled and everything. But can you just do an electronic thumbs up if you caught that I just gave you the answer for A, but I want to make sure, did you hear it? Like that part A is you draw 2 arrows and one's going to the origin, one's going away from the origin. Did anybody catch, or should I repeat it? Like, could you raise your hand if you did hear what I just said about the answer for part A? Thank you, Noel. Awesome. That's one person. I'm a little worried. So Noel got it. Did anybody else? Should I say it again? Did anybody else? I just gave the answer to A. Oh, thank you, Lizzie. Okay, thank you. So I'm going to go on. Hopefully, everybody else caught. All right. Because now comes the big thing. That's part A. Now, here's the honest thing. When I gave you, oh, and there's something in the chat. Sorry, wait. Oh, repeat. Oh, okay. Thank you for your honesty. Okay. So I'm talking about part A here. I'm talking about, part A of the second page of the extra credit thing. Part A says draw a neat and clear sketch of the situation. The sketch I'm looking for is a vector sketch. I'm looking for two vectors on an XY plane. One vector that is going to point from the point 5, 4, like, because I'm looking, see this chart right here. So you're drawing an XY plane, like you're drawing this plane here, but you're putting a point, you're putting charge 1 at the point 5, 4, like around here, if you can see what I don't know if you can see. And then you're putting charge 2 at the point like 10, 3, like, so like over, sorry, like over here. I don't know if you can see on the screen where I'm pointing, but you probably can't. But so you're labeling 2 points on the XY plane, and then you're going to draw an arrow, a vector arrow, connecting each one of those points to the origin, to the point of interest. The sketch that I want will have 2 vectors, 2 arrows in it. The key thing that I'm saying, the thing that I'm going to look for in the sketch, it's not hard, but it's not complicated, but it might be hard. I'm saying the vector that's going, the vector that connects Q1 to the origin should be pushing out, should be drawn from Q1 to the origin. It should point to the origin because Q1 is positive. It would push out. It would push on any 1 coulomb of positive charge that might be found at the origin. Like, we're trying to figure out what would happen to a positive 1 test charge at the origin. That's what it means to calculate the field at the origin. So we would want to know what happens to a positive if it were located at the origin. Well, from the Q1, the Q1 is positive, so it would push it. So there should be an arrow pointing from the coordinates 5, 4 to the origin. Whereas the Q2, which is at the coordinates 10, 3, it's a negative charge. So it would pull the origin. Like if we had a positive test charge at the origin, Q2 being negative would attract it, would pull it toward. So you should have an arrow. So the answer to the sketch in part A is that you should have an arrow pointing from the coordinate 5, 4 to 0, 0, but then you should have an arrow pointing from 0, 0 to the coordinates 10, 3. That's all I'm looking for in A, but that is what I'm looking for in A. But I'm just going to ask Elizabeth with an S. Did you hear, like, did you catch that? Did that work for you? I mean, that was the repeat. I don't know if it, and I know we've only got 5. We've only got 5 minutes. Wait, yeah. Okay. All right. Thank you. I appreciate it. Okay. Because now we only have 5 minutes. I'm obviously not going to do much in 5 minutes, but it's very important what I'm about to say. It may be even upsetting what I'm about to say. If you keep scrolling the sheet, if I keep scrolling the sheet, look right under part A. There's a part B that says compute the magnitude and direction of the E field at 0, 0. Okay. That is the part. I hope everybody's hearing me right now. That's the part that was accidentally left off the sheet on Monday when I handed it out. I didn't realize that's really the point of the whole sheet, to be honest. Okay. That's not a joke, part B. I mean, it's not, it's a kind of involved computation. It's kind of the purpose of the whole sheet, but it was accidentally left off the sheet on Monday. I didn't realize that until somebody pointed it out. As of Monday, it only looked like all you had to do was draw a sketch. And it would be kind of weird for me to give you 12 points just for a sketch. I'm asking you to compute the magnitude and the direction of the E field at part B. I didn't catch that until last night, or somebody pointed it out. So because I'm not trying to freak anybody out, but that does involve a little bit of work. That is why I re-uploaded the sheet. It's still all meant to be one sheet, but because that part B, which takes a little work, was left out accidentally initially, when I re-uploaded the sheet, I hope everybody's hearing me. That part is definitely required to get all these points, but I extended the deadline to Friday midnight instead of Thursday, And I changed it from 12 points to 14 points just to compensate you a little bit for your stress that I might have caused. But you have to do part B to get the points. Now, I'd like to sort of walk you through part B, but we only have 3 minutes left. So I'm not really going to be able to do it. Let me urge you to do two things. Number one, I somehow did manage to have more of a direct discussion of it in the other section this morning. So the YouTube is posted, or I mean, it will be, or it's uploading right now. I would encourage, I mean, you don't have to, but if you want to do this computation right, I'm not saying it's a trick and I'm not saying it's impossible, but it is an involved computation. So if you want to do it right, I really would strongly suggest watching the YouTube from this morning. It's called like EFieldAsVector Edition or something like that, or something like that. It's the most recent. Please watch that if you want to see how to do this computation. Number two, if you happen to have friends in that class or in section 3 that meets in person on Tuesdays, you could also talk to them. I mean, of course, you're welcome to talk to one another about this, and you could also text me questions. It's due Friday at night, midnight. Even if you get it slightly wrong, you're still going to get the points as long as you really do a thorough effort on this. But with 2 minutes left, I'll give you the overall sum. Well, actually, okay, I'll do a quick screen share. I'm going to quickly share the screen that I will put, like the thing I'm about to share, even if you only look at it for 1 minute, I'm going to put the PDF in, in Google Classroom so you can look at it more clearly later. I just want you to see. Okay. Yeah. This is a quick summary of, sorry. Okay. Yeah. I have 1 minute left. So I'm just going to summarize this whole thing. I hope you're listening right now. I mean, I hope you can hear this. It'll take a while to sink in, but I'm saying you got to get the total field. The question of this whole sheet is to get the total field at the origin due to both of those point charges. So what I'm really asking you to do is add those two field vectors that you just drew on your sheet. You're being asked to add two vectors. And this is where the whole R hat business comes in. The two vectors are given by that equation, that KQ over R squared. The way to add two vectors, you got to remember from Physics 203, and I know we're just about over, but the way to add two vectors is you have to take each vector, zoom in on it, and divide and separate its X and Y components, right? I'm saying this quickly, but you have to zoom in on each vector and treat each vector as the hypotenuse of its own right triangle. Again, you can play the video from the other class, but each vector is the hypotenuse of its own right triangle. So there's E1, like the field from charge 1, and there's E2, the field from charge 2. E1 has an X component and a Y component. E2 has an X component and a Y component. What your job is to get all those four components. You get all those four components and you add the two X components together, and that will make one big X component. You add the two Y components together. That makes one big Y component. So now you have one big X, you draw it, one big Y, and you do Pythagorean theorem to get the hypotenuse of the one big triangle that you create by adding the components together. Your answer that you're looking for is the length and direction of the final hypotenuse of a triangle that you made by adding components together. What I've done here on this PDF is I've just started you off by showing you how to get the first component, the X component of the first field. If you see what I'm doing there, or if you look later at the PDF and you get the point of what I'm doing, then you just do the same idea for each of the following components and you add them together. But again, you can watch the video from the other class, you can talk to people, but that's what I'm asking you to do. That's due Friday night for 14 extra points on the exam. I will keep pushing through and slowly dribbling your exams back to you one by one. I'm so sorry about all the delays. Thank you for being so engaged today. And I'm done. And I'm going to hang out just in case there's any more questions or anybody wants to write anything down, but I'm here. But thank you so much. And I'll see you next week. So goodbye. All right, thank you. Thank you.